Okay, so let's start. Welcome everyone to this first course in complex analysis that will take part during 15 lectures. So the course is complex analysis and it's 15 lectures. So this will be quite an intensive course. It will take part in the next 5 weeks, or for the lectures, the next 4.5 weeks. And it will be 3 times per week. So it will be Mondays, Wednesdays, and Fridays, always at the same time, from 9 to 10:30. And I know this is early. It's early also for me. I'm sorry about my schedule. It's not maybe optimal for everyone, except for the ones who like to get up in the morning. But, okay, so it's hard to get up, but I expect us all to be here. Okay, I will for sure be here, and I hope, you're also expected to be here. To be clear. And then there are also tutorials in this course, as in every course. So it's a 5-week course, and there will be 5 tutorials. But not the first week. So it will be lectures week 1 to 5 and tutorials week 2 to 6. Okay, so tutorials will be with Fernando Villegas, and the first one will be on Thursday next week. Okay, so I didn't check the time, but it is next week at some point on Thursday. And a very important thing, so practical thing, is that there will be hand-in exercises. Okay. So hand-in homework or exercises. Okay, and some of them will be graded, and this will happen every week. And the deadline is before the start of every tutorial. Okay, so deadline is before each tutorial. So the idea is that I give you these a lecture, and then I give you these problem sets with the first one will I think have something like 6 problems. And then you look at these problems and you're encouraged to collaborate, but each of you have to write your own individual answers on a piece of paper. And then you hand them in either in my pigeonhole or you hand them into Villegas at the beginning of the tutorial, and he will give them to me. And yeah, it's important that you keep the deadline, and then some of them will be graded. Okay, so this is to ensure that you do them and that you do your best, and that so I can see that you actually make progress and that you're following what's happening in the course. So it's important that you put some effort into doing this, and it will be quite intense. So far, you had I think only 2 courses going on. Now you will have this one added on, and then there will be maybe a 4th one. I don't know. But at least this will be quite a lot of added workload. So we'll have an intense month to work on. And of course, so this is my name. So you can call me, if you want, you can call me Zach. So my name is Zacharias, or simply Zach. And this is a Swedish name, so in the hymn you're the only one who haven't heard it pronounced. So it's Sjöström Dyrefelt. Sjöström Dyrefelt, yeah. So you can choose whichever one you think is easier to pronounce. Okay. So I think that's all for the practical matter. Well, except for one thing. So I've known everyone, with one exception already, for a few weeks, and I've asked some of you if you already took some complex analysis and so on, and I know some of you have already studied quite a bit of complex analysis. So I wanted to ask, who has already taken a course in complex analysis to get a more global picture of the class? You took one? Okay. Okay. And let's say who did not? Let's see if it's the rest.
No, I took the course of complex analysis, but it was not so intense. It was not so intense?
Yeah. Okay. Yeah, so probably, I'm assuming that not everyone saw exactly the same things, even, the people who raised their hands. But anyways, I wanted to tell you that I'm aware of this thing. So this has to be a basic course in complex analysis. So whenever I think of trying to do more advanced topics, there is one thing stopping us. It's that I cannot assume that you know various things about more advanced differential geometry or more advanced things that allow us to do really advanced complex analysis or complex geometry. But on the other hand, so it has to be a basic course because some of you may not have had complex analysis before. On the other hand, I have put quite a lot of effort into trying to plan a course that sort of is, I try to make, whenever possible, I'll try to go into more advanced topics and into maybe attacking the course with angles that you may not have seen before, so that everyone should see at least some new things each lecture, hopefully, or at least throughout the course. And then, of course, there are the problem sessions that I think will benefit everyone to do these problem sets. So this is my hope. But just so you know, I hope that you won't be bored for the people who took it before, and I'm doing really my best to try and make a course that covers everything basic for those taking it for the first time, but that will be interesting for everyone. Okay? So I'm trying a new angle, and I hope it will work out. I hope it will. Okay, and of course, whenever you have any questions, you know where I am. This is my office up in the math hallway. This is my email. And send me an email, come by my office, or Fernando's if you prefer, and I'll always be happy to help, okay? With anything that you need. Okay, so this is the basic setup of the course. Any questions so far on the practical matters? Okay, so I wanted to start in a way that maybe you don't always do. So usually a complex analysis course starts by telling you that the complex numbers are the numbers of the form A plus IB. Okay. But I want to motivate you a little bit, and I want to give you a global picture of sort of why you study complex analysis, and give you a short overview. Okay, so the point is that complex analysis. So I remember when I was a student, which was not terribly long ago. So I started doing research in complex geometry 5 years ago. And when I was a student and took the first course in complex analysis, I thought that this was somehow a course that was not like the others. It was a bit on the side, and it never interacted with the other courses, and you had all sorts of weird theorems, like all the integrals were zero or this kind of things, and you never really understood very deeply, at least me, sort of the point of this course. It seemed more like some kind of game. So why is complex analysis important? So complex analysis, so since I'm doing research in complex geometry, my first thought when someone asks me why it is important is that it is the local theory. So I will use some difficult words now and that you may not understand, and that's normal, okay, for the first 10 minutes, and then I will start from the beginning. So complex analysis is the local theory relevant for the study of complex manifolds. So here some of you may know, and most of you maybe may not know what manifolds are exactly, but you may have read about it. So complex manifolds is the basic object of study in complex geometry. So a complex manifold is a geometric object, sort of a generalization of the surface, okay? Could look, for example, like this, or it could be the sphere. All of these are basic objects of study in complex geometry. So this is called the Riemann Sphere, okay, of genus. In this case, the genus is 3. So this is an example of a compact complex manifold, okay, of complex dimension 1, and this is the sphere, which is the complex one-dimensional projective space, if you want. So just to put something on the board, make these drawings. Again, you don't have to understand at this point very deeply what these things are. So these are the basic objects of study. And in order to study these, the point is that locally they look like the complex plane. So if you take a point here and you take a neighborhood, then locally this will be isomorphic in the appropriate sense to C. Okay? And so when you want to study the local behavior on such manifolds, you have to study complex analysis. You have to understand how objects or functions, etc., behave locally near a point. So you need complex analysis. And then you go further. The next course, if you choose to continue in this world of complex analysis, complex geometry, would be to study how this works globally. And then you get a very beautiful theory that connects with algebra, algebraic geometry, that connects with analysis, and that connects to physics and various things. And since we are at ICTP, I think it's even more appropriate to share with you my favorite reason for studying complex geometry or complex analysis is that it is important, so it's important in mathematics, I will come to this, but it is important also in the real world, it is important in physics. So, you might think of these complex numbers, the imaginary number I, as something, a sort of abstract construction that you use for whatever reason. But really it has a very clear interpretation. So it's important in physics, more specifically according to string theory. So you have a lot of people in this building doing research on this. So you may or may not know that our universe, okay, so the universe that we live in is 10-dimensional. Did you notice? You may think our universe is 3-dimensional, but our universe is 10-dimensional. And what are these dimensions? Okay, so we have space, okay, 3 dimensions in our usual space. But I think you also know this, that we have space-time. So these are the 3 space dimensions, ordinary space dimensions, plus time, which we consider a 4th dimension in physics. So I don't assume that you know any physics, but you've probably heard about this. And these are 4 dimensions, 4 real dimensions, so 4 dimensions overall. So what are the remaining 6 dimensions that these string theorists have come up with that we have in this universe that we live in? Well, so these we cannot see. They are the internal dimensions in our universe, and they are accounted for by a so-called, so this is a very hyped word in the world of complex geometry and the world of physics. So it's a Calabi-Yau threefold. Okay, and what is a Calabi-Yau threefold? Well, it's a 3-dimensional complex manifold. So it's a 3 dimensions over C, but 3 dimensions over C is the same as 6 dimensions over R. So the remaining 6 dimensions are accounted for by a compact so-called Calabi-Yau manifold. So it's an object in this category of objects, let's say. So it's a complex manifold. So it doesn't matter what this means. It means a Ricci flat manifold. So it has a metric whose Ricci curvature is 0. You don't need to know what this means, but the whole point here is that, okay, even our universe consists of space and time plus 6 real dimensions accounted for by a 3-dimensional complex manifold. So it means that complex analysis, now abbreviated by CA because I will write it many times, is fundamental even to understanding our universe. Okay, so this is sort of my point. So the universe is in part a complex manifold. So if you want to understand how a universe behaves, you need to understand complex analysis. If you want to understand it deeply on a research level. Okay, and so you need to understand complex geometry. In order to understand complex geometry, you need to understand how complex geometry works locally near each point. And this course is about this. In one complex dimension, how do we behave close to each point? Then you can go globally, and then you can do it in more dimensions. Here you need 3 complex dimensions to understand our universe. Okay? So this is a journey, but this is where we're going. Yes?
If we take a point and a local neighborhood,
yes.
You say it is kind of like the complex plane.
Yes.
Why can't we consider it as R2?
We can consider it as R2. But if we consider it as R2, it's a less strong statement. So you see, what I'm saying is, when I say it is C, what I mean is that it is R2, but I also can introduce a structure of complex multiplication, so multiplication by the imaginary unit I. So this means that so complex manifold means you have a real manifold, so it means it's locally like R2, but on top of it you have something called a complex structure. So you have more information and more to work with. So you can say it's like R2, but if I say it's even like C, then I say something stronger than what you are saying. So it is entirely possible, but this is more information. Okay, so, I mean, for me this is, a good reason to get up every morning and do research in complex geometry. Okay, so this is where we're going. I also want to say a word or two about how it is important in mathematics, because some of you may not be, I hope that you like the motivation of understanding our universe. This is sort of a grand and beautiful thing, but it is also important in mathematics. So every year in the diploma program, there's always someone who's interested in number theory. Okay, so I will come to this. So analytic functions. So this is the basic study of the functions in this course that we will study are holomorphic or analytic functions. And they appear sort of everywhere in mathematics. So for example, I don't know how many of you attended these lectures on Fourier analysis a few weeks ago, but for those of you who did, I know some of you did, you will remember that we actually studied some analytic functions in this talk. We have harmonic analysis, and we have, maybe one of the most beautiful applications to mathematics itself is in number theory, which is, when Villegas gave this course last year and the year before that, so on. So he is doing research in such areas on number theory. And then in particular, so I should mention, if I mention the universe, I should mention another grand problem in this field. So, for example, you have all heard, of course, of the Riemann hypothesis. Okay? So the Riemann hypothesis deals with the Riemann zeta function. Have you heard of the Riemann hypothesis, by the way? Yes, no?
No.
Who has heard of the Riemann hypothesis? So the Riemann hypothesis, I think, is widely thought of as maybe the most famous unsolved problem in mathematics today. Okay. So it's an extremely famous problem. And this problem is in number theory. It's about, in the end, this is about understanding the distribution of primes. It's about understanding our numbers. But the formulation of a problem actually uses, so it studies the Riemann zeta function, which is this function, which is an analytic function, and this is my point. So it is defined as this integral from 0 to infinity of x to the power s minus 1 over e to x minus 1. Okay? dx, where gamma is the gamma function, so gamma of s is defined as the integral, also another integral, of x ds minus 1 e to minus x dx. Okay. So this looks super innocent. But one of the most famous unsolved problems in mathematics is about understanding the zeros of such a function. So here s is a complex number. Okay, so s here is a complex number. So you have some function of a complex number. And so it can also be defined by this. So this is an analytic function. It can also be defined as something called the analytic continuation of this sum. So sum of 1 over n to the power s for n equals 1 to infinity. So this is L of s. Okay, which is defined, I don't have to give too much details here, but the real part of s is greater than 1, then this kind of thing converges, and you extend this to all of C using something called analytic continuation. Okay. So I know that probably everyone in this room has no idea what I'm talking about, which is fine. I'm just trying to tell you that this is an analytic function, and one of the most famous problems in mathematics, and certainly the most famous problem in number theory, is about studying such an analytic function of a complex variable and understanding where the zeros are. And the conjecture is that all zeros are on the line real part of s equals 1/2. So yeah, so the conjecture is that all zeros of this z of s are on this line the real part is equal to 1/2. So all non-trivial zeros. Right. And this looks completely innocent, but if you understand this, then you understand a lot of things about the primes that we do not understand today. And you can solve many, many problems in number theory. Okay, so all of this to say that this is connected to many beautiful things, to physics, to number theory. Also, more concretely, it is very useful as a complement to real analysis. For example, if you want to compute integrals, so this I think some of you will know. In real analysis, you have some difficult integrals, like this one. And how do you compute it? Or how do you show that the sum of 1 over n squared, n goes from 1 to plus infinity, is equal to pi squared over 6, or such things. Complex analysis is very powerful to very easily show these things. Of course, I know this sum. You probably know already 5 proofs of why this is true. But there's also one in complex analysis, which you may or may not know. And often showing all these things in complex analysis is very natural, because when problems are difficult in real analysis, the real line is sort of inside the complex plane, and you can sort of go around the difficulty in a certain very vague sense. Okay, so the plan now, so the plan for the course is the following. So I will start with analytic functions and power series. So this is the first part of the course. Then I will go on to the Riemann Sphere. And Möbius transforms. Then I will study complex integration. So I think those of you who took already a complex analysis course, for sure they will have done number 1 and number 3. I think you have to do, everybody has to do something about differentiable functions in complex analysis and about integrating these functions. So this for sure you have seen on some level, but again I will try to do my best to introduce this from a more interesting angle for everyone. And then, time permitting, number 4 will be various bonus topics. Okay, so there are many bonus topics that you can study. You can study the connection to number theory, for example. You can study connection to harmonic analysis. You can say something about complex analysis in several variables. You can say many things. I will decide exactly what I will have time to say when I see how it goes and how fast we can proceed in the course. Okay, so this is the basic plan, and I should also tell you the book that you can use. So I'm keeping it Scandinavian for this course. So the book is by Alfors, so Lars Alfors. He's a Finnish Fields medalist. He was the first person to get the Fields medal in 1936. He's from Finland, and he wrote a book with the excellent name Complex Analysis. It's very suitable, and it's this book. It looks like this. Okay, so yeah, that's it. So I am, not following this book in order necessarily, but everything I say, or most things I say, will be in this book. And this is a very classical book for such a complex analysis course. So I recommend you to look in this. And if you have some other favorite notes or lecture notes from somewhere that you found online, or from your old universities, or from your friends or something, of course you can use anything you want. Okay? Okay, great. So now I hope that you're motivated but not scared by this introduction. If so, then I will have achieved my goal. So can I raise what's on the board? Okay. Okay. So, now let's start. So, since I have this ambition, oh my, this chalk is not good. So since I have this ambition of doing things differently, you know, at ICTP we have two kinds of chalk. There's the bad chalk and the good chalk. Someone put the bad chalk in here, I'm not happy. I will write with yellow because this is good chalk. Is this okay? Yellow is almost like white. So construction of C. So instead of just telling you, everybody here has seen, of course, in high school probably, for the first time, what are the complex numbers. So instead I want to sort of start from the beginning, tell you the story. So when you first go to university and you study classical analysis, so this is, can everyone see in yellow, by the way? This is fine. So in classical analysis, you work over R. More precisely, I write it like this: so R plus and dots, so with the addition and multiplication that you all know, of course. And this is an ordered field. Okay. And what does it mean to be an ordered field? So let me just recall. So it means that for any x and y in R, precisely one of the following statements hold. So precisely either x is smaller than y, x is greater than y, or x is equal to y holds. And on top of it, so maybe sometimes people tend to forget the second part of the definition of an ordered field. And the definition is that if x and y are greater than 0, then this implies that both x plus y and x times y are greater than 0. Okay, so this is just a definition of an ordered field. So far you have probably seen it. And then I have a very important remark. So there is one problem with real analysis. So everything, I mean, this is very good. You have an ordered field. This is something nice, something positive for your analysis. But you have a problem in real analysis, or an inconvenience, and it is that it is not algebraically closed, this field. So what does it mean to be algebraically closed? Does anyone know? Yes, exactly. So you cannot find solution to a polynomial equation. So of course, as you all know, this polynomial x squared plus 1 does not have any real roots. Okay. Because, as you also know, a posteriori the roots are plus and minus 1. Okay, so this one has no roots. Over R. Okay. So therefore it is not algebraically closed. So what people said, like 200 years ago, was, okay, we work with R. It's ordered, it's good, it is not algebraically closed. And then, I don't know how they started looking into this. Maybe they knew something, or it's just simple curiosity. But we started asking the question, so can we make R2, so this R2 with usual vector addition, it's an abelian group. So can R2, so this is an abelian group, so we view it as its abelian group, be made into a field. Okay, so this was the question. Can R2 with the usual vector addition, so this is R2, with two vectors, AB, then you all know how you geometrically add these vectors, A plus B. You also know how to do it in coordinates. So if we prescribe that this, we want this to be our addition, and we want scalar multiplication to be preserved, so into a field, so more precisely such that multiplication of a real number and a vector in R2 is preserved. Okay, so what do I mean by preserved? I mean that we want some multiplication. So we take two vectors in R2, and we want to say what it means to multiply A by B. So these two vectors, A and B. But we want it to be in such a way so that, you know, if one of these vectors were on the real line, so, you know, so we identify it with a real number in some sense, then it's just, you know, a multiple of this other vector, B. So we wanted to extend our usual scalar multiplication. Okay, so can this be done? And then another question, can we do it with Rn plus? You know, so of course we check first R2, and then, as we will see today, you can. So the point of what I will say in the next 20 minutes or 30 minutes is that you have no choice. If you want to do this, what you get is the field of complex numbers. And you can prove that this is the only possibility if you want to do this. Okay, so this is where it comes from. And then, if you want to do it for R3, or R4, or R5, or R6, then in general it is actually not possible. So, I mean, sometimes in mathematics, you know, you go to these courses and everything is sort of prepared for you and it looks like everything was easy. But, you know, these questions were actually difficult and it is not at all obvious, I want to underline this, it is not at all obvious that you can do this. It is kind of a miracle that you can do it for R2 and you get C, and C will be algebraically closed. But for R3, it is not possible. And if you do it for R4, then you can do it, and then you will get what is called the quaternions. And this is what Hamilton, the Irish mathematician, discovered in the 1800s. How you can define, how you can make R4 into a field. And then you can do it for R8, and you get something called the octonions. But for all other n, it is impossible. So this is kind of...
So it's possible only for R2, R4 and R8 only?
I believe so, yes.
But they prove that it's possible, it's impossible for the others, or just we don't have...
Yeah, so I would have to sort of double check this, but this is what I think, yeah, in my country. So for sure you have a famous one, 2, 4, and 8. And then, yeah, I'd have to double check, but I believe it's really not possible for the other ones. Yes, this was an improvised remark. Okay, so how can you make this into a field? Okay, so what do you do? So claim, so the first claim now is that if this is possible to make R2 into a field, then necessarily, oops, sorry. So let's still call this field R2 plus with some multiplication. So let's say you have constructed some field here. This field will be C, okay? But for now, let's pretend that we don't know it. So then there will exist some element here which squares to -1. And of course, -1 is something that makes sense because I tell you this is a field. I assume it's a field, so it has to have a neutral element for multiplication. And this neutral element for multiplication is 1. And this neutral element for multiplication has to have an additive inverse because I assume it's a field. Okay, and this additive inverse of the multiplicative neutral element is what I call -1. Okay, so this is what I mean by z squared equals -1. And I mean, this is kind of striking, and this is an example of something I think you don't usually see in complex analysis courses, but it is very nice. So let us try to solve this exercise. That there has to be such an element. You have no choice. And this will really explain to you, so I think this is nice because it will explain to you why you get this number I that you will work with later.
Sorry?
Yes.
The claim is this is a field?
Yeah, if you can make this abelian group, R2 plus, with the usual vector addition, into a field, then you have no choice but to have an element that squares to -1. Okay, so how do you see this? So choose a basis, let's call it 1 and E. So what I'm doing is I take 1, as I told you, I have a 1, the multiplicative neutral element, and then I take any other element that I want. So E is not a neutral element, I'm just calling it, it's any other element in the field. but that forms the basis, because we know R2 is a vector space of dimension 2 over R. So I can do this, okay? So choose a basis of R2. Okay, so then, what does this mean? So I take any element, Z, and then this element is of a form x times 1 plus y times e. Okay? And in order not to, to make the notation easier, let me just write it x plus y e. Okay? So any element has to be of this form. And now what happens when I square it? So what do I get? So I take x plus y e squared. Okay? So I will get x squared, so x squared times 1. Okay, and then I will get plus 2xy times e. Okay, so this is not, this is the scalar multiplication. So 2xy times e. And then I will get plus y squared times e squared. Okay, and what is e squared? So e squared, a priori you may wonder what is the meaning of e squared, because I just told you it's an element, so it's a vector in R2. And I'm telling you I'm squaring this vector in R2. Okay, so there's a simple solution to giving a meaning to this thing. Well, we know that any element can be written, using the two basis elements. So in particular, e squared can be written using a linear combination of 1 and e. So let's call it a plus, so a times 1 plus b times e. Okay? Sorry? Yes, thank you. E squared is equal to this. So what you get then is that z squared, so you replace this by this, and you get that z squared is equal to x squared plus ay squared, okay, and times 1, okay, let me write it out just for once, and plus 2xy plus by squared times e. Okay. Is this correct? So of course, I made this calculation yesterday, and now I'm writing it on the board, but we should check that this is correct. Okay, and now what I want is to show, that I can pick x and y in R2, okay, such that, so x and y are both real numbers is what I mean by this. So maybe this is confusing. So let me write, there exists x and y, both in R, such that z squared is equal to minus 1. And we have that z squared is equal to this. Okay? So if you just look at this, it is not so obvious. But there is an obvious way to start, at least, tackling this problem. So what would you do? Okay, any ideas? So this thing has to be equal to minus 1. So this means that, in particular, this component of in front of e here, it has to be 0. And this thing has to be minus 1. Okay. So this has to be 0, so this already gives us two options. So we know 2xy plus by squared equals 0. Okay, and this gives two choices. So this implies that either y equals 0 is the simplest possibility. Okay. So if we take y equals 0, then what happens? Then this is 0 and this is x squared times 1. And this is always positive. Okay, so why is this always positive? So if we want to be really sort of rigorous, which we should, then we should show that, okay, x is a real number. And we know that R is an ordered field, and in any ordered field, the square of a positive number, of any number is positive. Square of any number is positive. Okay, of course. R we know very well. So it's not just an abstract ordered field, but we know that this is positive. So this is not possible, okay? So this is not possible. Not doing what we want. Okay, not what we want. If you understand what I mean by that. So it's a possibility, but it's not making us happy. And the other one is that there is another solution to this. And that solution is that x is equal to minus b squared times y. Okay, so I write it like this. Okay, so y is equal to 2 over b. So x equals minus b squared times y. Okay, so let us assume this and see if this, if we can get z squared is equal to minus 1 using this. So then what do we do? So assuming this, so now we assume that x is equal to minus b squared times y. So then we can put it in here, okay, to z squared. Then what we get is that z squared, so let me read here from my calculation, it means y squared plus ay squared. So I introduce it to times 1, and then we have plus 0, which is the point. So we did all of this so that this part will disappear. 0 times e, so we take this away. Okay, and then what is this? So it is equal to a plus b squared over 4 times 1. Okay, so now the question is, what is the sign of this a plus b squared over 4? Okay. So the next claim that I have, which I think is not very obvious at all once you see it, but the proof is easy. So this has to be negative. Okay? It has to be negative. Why? And this is because R has no zero divisors. Okay. So if A times B is equal to 0, then A is 0 or B equals 0. So why is this? So let's assume not. So proof of this claim is that, so if we assume instead that A plus B squared over 4 is actually non-negative, then we can actually take the square root of this thing, and it's well defined, because we can take the square root of a non-negative number. Okay, and then we would get that z minus y is the square root of a plus b squared over 4 times z plus y times the square root of a plus b squared over 4. Okay, so we look at this, and this is actually equal to 0. Okay.
There is a y square missing.
Is there a square missing?
In the third line.
On the third line. Which was this?
No. Over the, yeah.
Here.
Yeah.
Where is a square missing? It should be
Y square.
y squared.
No, outside.
Outside, y squared, okay. Yes. Indeed, yes. Y squared is missing. Okay, thank you. So y squared, and then it means, yeah, exactly, okay. But here I wrote it correctly. I just didn't copy it from my notes. Okay, very good. So, of course, so we had z squared is equal to this. So you put z squared minus this is equal to 0, and then you can factorize it in this case, in this way, in a standard way, using conjugate root. So this would be equal to 0. Okay, but since this, since the field, actually it's not because R, but because of field, fields have no zero divisors. So since fields have no zero divisors, then one of these two factors has to be 0. Okay. So one of these two factors are 0, but is this possible? Okay. And the answer is it's not, but neither factor is 0. And why is that? Does anyone see it? So what is the only possibility if it's 0? The only possibility if this thing is 0, I mean, if you have a complex number and it's 0, then in particular where e component has to be 0. So you know we wrote it as a sum of, in the basis 1 and e. So the e component has to be 0, but e component is 0 means that y equals 0, because you remember that we wrote this number as x plus e times y. This means that y equals 0, and it means that we were already in the first case, so this is a contradiction. Okay. Contradiction, and the conclusion is that in the second case, when y is not 0, but when x is equal to minus b over 2 times y, then you actually have that this thing is negative. Okay.
So how did we get the contradiction?
Sorry?
So how did we get the contradiction?
So yeah, so now we prove the plan.
Yeah, how did we get the contradiction?
So we got the contradiction by saying that, so the product of these two things is 0, which means that one of them have to be 0, but this means that the e component of these numbers have to be 0, and this means that y has to be 0. And this was a contradiction.
If the e component of this number is 0, and y is then is 0.
Yeah, so you remember that y, so z, so maybe this is the, so z is equal to x times 1 plus y times e, is what we said in the beginning.
And the other side has no e component.
Yes, so I mean, so we're using this, if you remember that y was coming from this,
Yeah.
and this is, you see this, and you get the contradiction, okay? And then, okay, so why do we use this? So this thing is negative, and then it means that we can look at the square root of minus this thing. Okay? So now, because this is negative, we can set, so y is equal to 1 over minus, the square root of minus a plus b squared over 4. So now this makes sense. Of course, this square root is now a square root of a positive real number. So I can define this, and again I take x is equal to minus b over 2 times y. So this was the whole premise I had, so I just remind you that we had this. So using these two, okay, so now the claim is that using this, we just have to input this in our formula for z squared, which is here. So a plus b squared over y times y squared, and then we see that z squared is equal to, okay, which is equal to minus 1 over a plus b squared over 4 times a plus b squared over 4. So you do this calculation, and you see that actually this is equal to then minus 1. You see, minus 1. So this is equal to minus 1. So of course, okay, now you have to look at it maybe to realize that you have to take these numbers, but now I'm telling you that since we have this claim, you can take these numbers, and then it's of course a trivial matter to check that z squared is in fact minus 1. Okay, so what have we done? We have said if we assume that we can make R2 with this usual vector addition, so we want addition to be this vector addition of elements. So if we can make this into a field, then we have to have an element z such that z squared is equal to minus 1. In fact, we will have exactly two such elements, but we are not proving this, okay? So we have to have an element such that z squared is equal to minus 1. Okay, and what do? Well, we take one of these elements that we now know exists, and we call it I. Okay? So this is what we do. Okay. So now pick such element in this thing. Note, by the way, that we have not yet proven that it is possible to make R2 into a field. We have just shown that if we assume we can make it into a field, then there has to be an element with squares to -1. Okay. So, but still, I mean, assume that we have this. So then, well, so if it is possible, then we would have such an element. And now pick this z here, such that z squared is equal to -1. So this is sort of the philosophy. And then call this element I. Okay? Call it I. And this, so actually everybody says imaginary number for this thing, which is our terminology. But so this is the what Gauss in his thesis he called it ideal number. Actually, he thought it was the ideal number that you could introduce, because if you introduced this number, you could find roots to all the polynomials. Okay. So in this sense, he thought it was an ideal number, and this is why it's called I. Then it somehow turned into imaginary with time, for some reason. But so it was ideal number, and this was introduced by Gauss in his thesis. Okay? And the motif of introducing this was that he wanted to deal with general polynomial equations. Okay. This is why he introduced this. Okay, so as I said, so I underline, we have not shown yet that it's possible to make such a field, but of course this is a sort of trivial matter, so the exercise is that this defines a field. Of course, everybody in this room knows how to check that something satisfies the conditions of being a field. So this defines a field that we will now, for the first time in the course, finally call it C, the field of complex numbers. And this field is defined, so there are many ways of writing it, of course, and introducing it, so like we have just done. So C is the field of real numbers, where you do a field extension with I. So I will tell you what this means. So this is simply the notation for the set of A plus BI, where A, B, and R, and I squared is equal to this element. Oh, shit. Well, okay. That's equal to -1. Yes, so, and, checking that this is a field is a trivial matter. So, okay. This is not on the homework, this is too easy. Okay, and this is also equal to, so this is worth noticing. So this is the ring of all polynomials with real coefficients in the variable x. And you quotient this by x squared plus 1. So this is actually also equal to this, because this is in fact equal to, a plus bx, all the representatives of these elements in this polynomial ring. Okay, and the fact that that x that lies in this quotient means that x squared plus 1 is 0, so this x here squares to -1 in some sense. Okay, it's a root of this polynomial. X squared plus 1. So it's equal to this. So these are all the polynomials over R. And this then defines our field. Fine, the field of complex numbers. Okay, so have you seen this before? How you sort of construct, or where it comes from, this C? Okay, very good. So let me see, so this, what do we get? So we get a field. So the miracle, the great thing with this field, is that C is algebraically closed. Okay, as I have said already multiple times. So this is a great thing. You can solve all the equations. This simplifies life. So formally, this is of course, the fundamental theorem of algebra. So I should just write it on the board. Fundamental theorem of algebra. Okay, and it says that if you have some polynomial in any p in this polynomial over C, and assuming that it's a non-zero polynomial, well, non-zero. Doesn't matter.
Non-constant.
Also zero is possible.
Non-constant.
Sorry, non-constant is. Non-constant. Thank you. That's what I meant. Non-constant has a root. In C. Okay, thank you. Okay, so any non-constant polynomial has a root in C. This is a fundamental theorem of algebra. And then I have the second thing I want to say, so remark and warning, you know. It does happen that you see people make this mistake. It's not a good mistake. So, this is not an ordered field. So R was not algebraically closed, but R was an ordered field. So now we win something. We get the fundamental theorem of algebra, but we lose something. It is no longer an ordered field. Okay, so if I give you two complex numbers and ask which one is bigger than the other, then you know you can not answer this question in general. Okay. So it is not an ordered field, and moreover, it is not. I mean, this is not just something that happened by accident, but you can show that it is not possible to make R2 into an ordered field. So there is no way of making it. It's not just that we haven't found it, but you can prove it is possible. It is not possible to make it into an ordered field. So the proof of this, so the argument, is that suppose that C is ordered, okay, for contradiction. Let's see what would happen. So then you can show, so this is a little exercise to show that any, I mean it's not hard, but in any ordered field, so if you take a completely abstract ordered field, satisfies these two axioms, then for any such thing, if you take the square of an element in an ordered field, it is positive. So any square is positive, but now we have, in C we have some interesting squares that we don't have in R, that has some interesting behavior. But then, you know, in C we have 1 squared, which is equal to 1, and we have I squared, which is equal to minus 1. So if I take 1 squared plus I squared, then in an ordered field, this should be positive. But it is not. It is equal to 1 minus 1, which is equal to 0. And we get contradiction. So there's no way to put an ordering on it, because then this thing would have to be positive, but it's not. And there's no way to choose, I mean, there's always this element, as we have shown, I mean, now I spent 20 minutes showing, but there has to be an element that squares to minus 1. So this argument will always happen. There's no way of making the field C into an ordered field. Okay. Yes.
Why, if the field is an ordered field, then the summation must be greater than 0? So
this is an axiom. So you remember I wrote in the beginning, I said R is an ordered field. This means that if you have two elements, then one is bigger than the other, the first one is bigger than the second, or they are equal. And the second axiom was that if you have two positive numbers, then their sum and products are also positive.
Yes, but here, why do you consider them as positive numbers?
Because of this thing I just said. So this is an element in C.
Yes.
So I and 1 are both elements in C. Okay?
Yes.
And assuming it is an ordered field, the square has to be positive. So this is the...
No, this is the point. Why, if it is an ordered field, then its square must be positive?
Yeah, so that is the sort of claim, that is the exercise. To show that if you have the axioms of an ordered field, then the square must always be positive. There is no choice but to do this. And thanks to this exercise, that the square always has to be positive, if you have an ordered field, then you get this contradiction. Yes?
Is it the square of non-zero element?
Yeah, sure. Absolutely. Thank you. Square of non-zero. These two are non-zero. Very good. You should be precise in mathematics. Okay, so it cannot be made into an ordered field. And then I have already made this remark about how R3 is not possible to make into a field at all, and I made this remark that R4 can be made into the quaternions. So I don't have to write this again. Okay. So instead, that was sort of the introduction. Now we have constructed the complex numbers. Any last questions before I erase? Start with this. Oh, and by the way, this fundamental theorem of algebra you can prove very nicely using complex analysis. So at some point during the course we will see this proof. I'm not completely sure yet if I will do it on the board or if I will give it as an exercise, but either way you will see it when it is time. Okay, so now we're going to start the actual course in some sense. You know, most complex analysis courses start here. They say, C is just A plus IB. But now you know what, okay? So, geometric representation of complex numbers. Okay, so let's now do the basic recap of things that everybody knows, but it's still very important that everybody really remembers them, so we have to do it. Okay? So we do a basic recap. So first of all, so C is a vector space of dimension 2 over R. Okay? This is very clear. So as you remarked earlier, why can we not say it's R2? Well, as a vector space, it's R2. But we have this structure of a field on C that is not implied when we just speak of R2. Okay, so we have this multiplication of I. And any complex number, so this is the so-called standard form. So any complex number can be written like this. This is standard form. So yeah, I think it is useful to introduce some of this terminology because people may have been used to terminology in various other languages. So here it is in English, not in French. And so then you have the conjugate. Okay, so this is the complex conjugate, which is A minus IB. So of course the picture is this. So here you have Z equals A plus IB. The basis vectors are here 1 and I. And so then here this height here is B, and this side here is A. And then if this was our element, then this is the conjugate Z bar. So all of this I think you know extremely well since many years back. And then sort of important remark in complex analysis is that if you take the absolute value of such a complex number, of course you know what this means, it's the same as taking absolute value of a vector, then this is equal to Z times Z bar. So this is an important thing to recognize when you concretely manipulate things in exercises, when you manipulate complex numbers. Okay, so this is A plus IB, so it's very easy to see, times A minus IB. So it's equal to A squared plus B squared, which is then, of course, the absolute value squared of such a vector. So absolute value is absolute value, it's greater than or equal to 0. And we have equality if and only if Z is equal to 0. And of course this thing here is the Euclidean distance from Z to 0. Okay, so I hope this is a very easy recap for everybody. And then it is, however, worth remarking about how do you divide complex numbers. Okay, take the multiplicative inverse of a complex number. So if I want to write 1 over z, then what is this? So I'm sure many of you know the answer, but a very useful observation is that it is equal to this. So I multiply by the conjugate, z bar, and both in the numerator and the denominator, and I get this. So for example, if I give you a number like 1 plus 2i or 3 plus 4i, and you want to write this in the standard form, like a plus ib, what you do? Well, you say this is equal to 1 plus 2i times 3 plus minus 4i. Right? So you take the conjugate, and over the absolute value of this number, which is 25, okay, and then you see whatever this is, okay. So it is equal to something like this. Okay, so this is how you do it. I thought it's worth to just show this once, so nobody is stuck on such a little trick. So this is very useful and very necessary to know. Okay, and also a simple exercise to check. So check that z plus w conjugate is equal to z conjugate by w plus w conjugate. I mean, I think it's good to recall this because honestly, I feel that many people, they tend to be very unsure about what we can do with the conjugate, what are the rules that you are allowed to use when you manipulate the conjugate. But so this is true. The sum of the conjugate is the conjugate of the sum. And you have also with multiplication. Okay, and what was the last one? I wanted, so this is related. It is about the absolute values of the number. So you have all these properties. Okay, so far, just clear. Of course, this is trivial to check. Okay, and then we have also, the polar representation of complex numbers. So is that you can write the complex number in this form, as you very well know. So again, if I draw a picture, it is, if you have some element here, z, then instead of saying that, okay, it's A and B characterized by this distance, you might as well say it's the angle counterclockwise from this thing, and then it has also a length. So here, R is equal to the absolute value of Z, and theta is what we call the argument of Z. Oh, by the way, I forgot to tell you that, of course, if Z is equal to A plus IB, then A is called the real part of Z, and B is called the imaginary part of Z. This notation, I hope that you recognize. So I have to tell you this. Okay, and you have this formula, and of course you have Euler's formula. Hang on. So I should tell you one thing first. Okay, important thing about complex analysis is that this argument, so theta here is not unique. Okay, so of course it is 2 pi periodic. So if I take theta to be pi or 3 pi or 5 pi or minus pi, it's always the same. Okay, so it's 2 pi periodic. So this is extremely important, and this sort of it is something unfortunate sometimes in complex analysis, but it also gives many opportunities for some nice tricks. I mean, sometimes it's actually a positive thing that this is not unique. So as you will see later in the course. But it's definitely something that you need to keep in mind, that this one is not unique. And this was a big problem that they were thinking about through history and development of complex analysis. And this is not unique. Okay, so we also have, sorry, I should use yellow. So Euler's formula. Okay, so as you all probably learned in high school, e to the I theta is equal to cosine theta plus I sine theta. Okay, have you seen this formula before?
Yeah.
But this is kind of definition, right?
No, it's not so. I mean, so the definition that you will see is that e to the z, so this is defined, I like to think of it as power series to be the main kind of definition. So this is equal to the sum of z to k over k to k, okay? K from 0 to plus infinity.
No.
So this is how it's defined. Okay, so e to the I theta. So actually, many of these things that I will claim to you, I mean, I will recall these rules and I will talk about power series and integration, differentiation and things like that. And many rules look very familiar to you. Like I will tell you, the sum of differentiable functions is differentiable, or if a function has derivative vanishing in a neighborhood, in a small ball, then it has to be the constant function. These things sound like complete trivialities, and maybe you wonder, why are you even sort of listening to this after having studied for already several years or at university, okay? But the point is that in complex analysis, the proofs are completely different. So really what should be interesting to us is to look at sort of the reasons why these things are true. And some things would sound very easy, like this thing, like derivative 0 means you have a constant function. I bet if I asked you this, to prove you this right now, you couldn't do it. I mean, it's not that trivial. So you will see why. So really the proofs are how you understand the subject, It is one thing to sort of recognize the statements, but you have to be able to prove and understand more deeply a subject. So even when I tell you these trivial things, like, okay, yeah, we saw this in high school, this proof is also very easy, but it's important to understand always where it comes from. So in this case, e to the I theta, so what is it equal to? So let me just write this very quickly. Okay, and so on. And so this is equal to, so it's equal to 1.
Factorials.
Yes, factorial. Thank you. 1 factorial. 2 factorial. Thank you. So it's equal to 1, and then it's equal to minus theta squared over 2 factorial, and so on, plus I times, and then what do we have? We have I times theta minus theta cubed over 3 factorial, and then so on. And this thing here is exactly what you know from real analysis is the power series expansion of cosine of theta, and this is the power series expansion of sine of theta. So this is the proof of this formula. So so I wouldn't call it a definition. I mean, it's
actually,
yeah.
When I took the complex analysis course, we defined e to power z.
Mm-hmm.
We defined it this way.
Okay. Yeah. So I would much prefer to think of the definition of e to power z as using the power series. And the definition also of sine of z and the cosine z and all these functions using power series. I think this is the best way to think about it. And the reason why I think this is the best way is because all of these are complex differentiables. So this is what we call holomorphic or analytic. And there will be, the most basic, the first really important theorem in complex analysis is that all the holomorphic functions can be expanded as power series. And every function that comes from a power series is complex differentiable. So this is an equivalence. So really the basic object of complex differentiable functions is called holomorphic or analytic functions. This is synonymous. These are exactly the ones that come from power series. So really I think the natural point of view on complex analysis should be to think of all the analytic functions always as power series. Okay, so this is the reason for this. So yeah, so you have this formula. And of course you have very simple geometric interpretations that you're used to. So if you have Z1 is R1 e to the I theta 1, z2 is equal to r2 e to the I theta 2, then z1 times z2 is equal to r1 r2 e to the I theta 1 plus theta 2, which means that if I have two complex numbers here, so I have z1 with angle theta 1, and then I have z2 with angle theta 2, then when I take z1 times z2, then I add the angles together, okay? So I will get something which is maybe here, and then it will also depending on how long this is, I will multiply the absolute values. So I don't know if this is now greater than 1 or smaller than 1. Let's say that it's all smaller than 1, so it actually gets smaller. Anyway, this is theta 1 plus theta 2, and the length of this is the product of the lengths of the other vectors. Okay. You're not shocked that it looks shorter, right? This can happen. The length of the other vectors is 1/2, and it's 1/4. So this is the simple thing, and this also illustrates very clearly that e to the I theta plus any integer multiple of 2 pi, so k here is any integer. Okay, so this is equal to e to the I theta. This is what I want to do. Okay, this is extremely important. Never, please, make a mistake forgetting this in complex analysis. Okay. So now I have told you about the basic things. So now let us go. Let's see how much time we have. Okay. So let us start talking about complex differentiation. Okay, so now this is the first, really fundamental section in any complex analysis. So this is differentiation. Again, this will be about holomorphic or analytic functions. Who has heard at least one of these words before? Everyone? And who has heard both of them?
In my interview, I heard about holomorphic.
In your interview? Yeah, I was doing the interview, so I should remember that. Yeah, exactly. So anyway, this is important just not to make you confused. So holomorphic means complex differentiable. Okay, analytic means that it can be written as a power series. Okay? And then there is a theorem. This is the same thing. Okay, so, really I like to think of the fact that there are these two notions. There is the holomorphic function and there is the analytic function, but then they happen to be the same thing. After studying this for 30 years, we managed to prove maybe this theorem that actually every holomorphic function is analytic and every analytic function is holomorphic. So now, 150 years later, people just say, let's not confuse the students, let's just call everything analytic, or let's just call everything holomorphic. And this is why some of you may have only ever heard the word analytic, because the word holomorphic becomes redundant. It's not necessary because it means the same thing as analytic. But it is really a theorem that it does. So for me, I like to remember this theorem by remembering both the words. Holomorphic means complex differentiable, analytic means you have the power series, and this is actually equivalent, but this is the theorem. Okay, so this was the explanation, so you will see this theorem later. So in order to talk about differentiability, we need to introduce some kind of metric structure as well, right? Because in order to talk about differentiability, you need to talk about open sets or about having some kind of metric. So it's a metric space. And what is a natural metric on C? Well, it's just using the absolute value, take V. And this is exactly what you did, in linear algebra. This is in the sense of vectors in R2. And then you have, as you know, from linear algebra, you have a triangle inequality, which holds also in this setting, just the same. And then you have topology given in the usual way, where open disks. So you have an open disk. It's this set of all the complex numbers such that the distance is less than some r. Okay, and I call this the disk of radius r centered at w. And I write it like this. Okay, so this is an open disk. Here's w. This distance here is r. And then you have some z. So this is the open disk. Then you have a closed disk defined in the same way. Okay. So closed disk. Okay, so we set complex numbers such that this is less than or equal to r. Okay, so you do it in this way. And now definition. And all of this you know very well in the real setting, of course. So a subset of C is said to be open if every point in this open set has a disk of radius epsilon for some epsilon positive. Okay, so the picture is, of course, very clear. You have some set like this. It is open if around every point you can find a small disk, open disk, which is still inside. Okay, so of course, nobody is very impressed by this. It's very easy. Okay? Now the definition of differentiability. So let's go into this. Okay, so you have these functions. So let's start by just discussing what are functions on C. Okay, so you have some function from C to C. So really, we can also view this using functions in R2. So it can be viewed as going from R2 to R2. And we can write f of z. So we can write this in standard form using the coordinates x and y. So the pair xy will be in R2. And we can write this as u of xy plus I times v of xy, where now u and v are functions from R2 to R. See, so we can view it like this. So this will be important soon. Okay, and so now consider differentiation. So for differentiation, we consider all this very familiar stuff. So, okay, let me just tell you. So A in C is an open subset. Okay, and small a is some point in this subset. And then you consider f of a plus h minus f of a divided by h. Okay, again, now we're back in high school. But let me just make one remark. So the only difference here is that h is now a complex number. And this is an important thing not to miss. So h is now a complex number. Okay? And so definition, I'll do it first. So say that f is differentiable at A if the limit as h goes to 0 of this quotient exists. Okay, and of course, what does it mean for a limit to exist? So this means that for every epsilon there is a delta such that okay, so the limit of g of z is equal to L as z goes to A. So this means that there exists a delta such that g of z minus L is less than epsilon for all elements such that are close enough to A with respect to this delta. So as you know. Okay, and the definition here, so denotes, so it's differentiable if this limit exists, and denote the limit by the usual notation that you would expect, f prime of A when it exists. Okay. So now you do it. So this is the definition.
We are supposed to take an open set, why we cannot take arbitrary subset?
So I mean, if you took an arbitrary subset, then you would have problems in giving the definition on the boundary. So you see, this definition of differentiability requires you to be in a point where you can move a little bit in every direction and see how the function changes. So if you were on a closed set, that means you could take a boundary point and then you cannot move in this direction. Okay, so mathematics has evolved into giving meaning to sort of derivatives also in this kind of sense. But the standard notion of derivative that you used and that we want to introduce really only makes sense if you can take a small neighborhood and go and change in every direction. Okay, and so, yeah, the time is almost up. So I will not have time to prove the Cauchy-Riemann equations today, so I will have to mention them on Wednesday morning, which is the next time that we meet. But really, so the point of this complex differentiability is that it is very different notion from the real differentiability. So for a real function, a function of real variable, to be differentiable is something, I mean, it's not an extremely strong condition. So all you need is for this limit to exist here on the real line, and you need the limit to exist when you come from the right, and you need the limit to exist and be the same when you come from this direction. But in the complex plane, this limit has to exist when you come from any direction in the complex plane. And not only from straight lines, but you have to be able to come from like a path or anything, right? So in any way that you approach this point A, where we want our function to be differentiable, any way we approach it, the limit has to exist and the limit has to be the same from every direction. So instead of having just two directions, now there are many directions in which it has to be the same. And so really this is a very strong condition, and it is so strong in fact that this, as we will see later, turns out to be equivalent to actually coming from a power series. So being complex differentiable is a rather strong condition in contrast to being real differentiable. Okay, so today then we have, first I have presented you some motivation about how complex analysis is the local theory of complex geometry, which allows you to understand our universe, which I think is great motivation. And then we have seen how to construct this field of complex numbers. And we have seen that this is the only possible construction, essentially. I mean, any construction you do will see this number which squares to -1. And this becomes a field, and there is no way of making it into an ordered field. So I want you to remember this. And then, okay, we had time to at least give a definition of a differentiable function. Oh, by the way, so I can say that, I can say the last meaning, but the last sentence. Definition of holomorphic. So I can add this, there's just one more sentence. So say that f is holomorphic if it is differentiable, well, holomorphic on A, if and only if f prime of A exists for every point in this set A. So this is the definition of holomorphic function. I hope you can see. And I think it's important to remember this remark that holomorphic and analytic will mean the same thing, but the original definition of holomorphic is this. The original definition of analytic is the power series one. Okay, so let's stop and see you on Wednesday.